Hello, welcome back. So, today we will be talking about something. I wasn't too sure whether I should include this or not. It is a little on the theoretical side. But nonetheless, I thought it's a good idea that at least you see it once. So, the idea of time domain analysis in this state space form, and specifically a concept called state transition matrix. So you'll see it often when we're talking about dynamical systems, especially these linear systems. So let's begin. And I warn you, this is going to be a little kind of dry and theoretical without too many pictures or figures. So be prepared for that. So I have usually this system, either the linear form or nonlinear form. I have x dot equals ax plus bu, or my state vector as a function, as a vector function of the current values of x and u. These equations are extremely well suited for numerical analysis. So if I know my current x and my current u equivalently here, I can very easily calculate the derivatives of all the state variables and use any kind of numerical integrator. The simplest one would be the new x would be x dot times dt, just taking a tiny step and then update the x value based on that small change and essentially march forward in time and calculate any kind of response to any arbitrary input, even in its more complex nonlinear form, which we usually don't have a closed form solution for. But nonetheless, despite the fact that we can very easily numerically calculate the response of the system, let's try to take a little bit of analytical approach and find the response of a system due to initial condition, the natural response, and due to input, the forced response. To do that, let's start with a simpler case that we are familiar with. Let's start with the scalar version of this. So I have x dot equals ax. For now, assume there is no u, so I'm looking for the natural response due to initial condition given x naught. So these are all just scalar values. And in your differential equation course, you may remember that one way we can solve this problem is to use Taylor series. So pretend I have this x of t. It is a function that I don't know, but I can write it as a series, as a Taylor series of unknown polynomials. So b naught plus b1t plus b2t2, and so on. So we can essentially approximate any or write any function using a Taylor series. Now the question becomes, what are the b values that satisfy this equation? So the first one, b naught, is easy. If I put t equals 0, so all of these ones that have time in it will be 0, so I'll have, the only thing left is b naught, and that is my initial condition, x naught, right? So that's good. At least I have one of those. To calculate the rest of them, we can take the derivative of this. So x dot of t. Taking derivative of it is easy. B naught is a constant, it goes away. Derivative of this term is b1. Derivative of that term is 2b2t. Plus next one will be 3b3t2, and so on. Now I can plug this into that equation. I have x and I have x dot. I can plug both here. So on the left hand side I have x dot. So b1 plus 2b2t plus 3b3t2 and so on equals a times that. So equals a b naught plus a b1t plus a b2 t2 and so on. To find the right values, I can check the coefficient of each of these t to the power whatever 1, 2, 3 and try to find a relationship between b's and a. So at the scalar one, I have b1 equals this one ab naught, and I know the value of b naught, which was x naught, so I have a x naught. Good, so I calculate b1. Next one is 2b2 equals ab1, which I just calculated. ab1 is ax naught. Well, let me write it this way. What do I want? b1 ax naught, which is, well, let me take, now I have 2b2. So my b2 becomes 1 over 2 a squared x naught. And I can keep going. The next one, 3b3 equals, what do I have? ab2. I have b2, so then I divide it by 3. So I have 1, 2 times 3. I have a cube, x naught, and so on. So now you will start to see a pattern. That my bi, the ith value, is going to be 1 over I factorial a to power I x naught. And now going back to this form, all of these bi's have some x naught. So I can, x of t, I can factor out 1 x naught. What do I have? Well, let me write it in summation form because it's easy. Summation, I don't like these markers. Well, I like them for one way, but I don't like them in another way. I do this. So summation I equals 0. This is to infinity. So b naught is that 1 over I factorial a to the power I that. And this is a familiar term. If you remember, this is the Taylor series expansion of e to the at. Let me double check, something looks not correct. Yes, I'm missing the t's. What? No, wait. Yes, ti. Yes, that's better. So my solution in the end, x of t is x naught e to the power at. So right, this is the way we could solve this from the known initial condition and differential equation to get to this form. We already knew it, but the process to solve it was important, and I wanted you to remember how we can get to this solution through Taylor series expansion. That was a scalar example. Now it's time to go back to the matrix form. Okay, so I have now, let's start from here. Let me write it as x. What is it better to do vector? X dot equals ax. What do I do? Let me write it as capital, so I don't have to worry about confusing it with the scalar case. So I have the same form, but in a matrix format. I can do exactly the same thing. So I know the initial condition, x at 0 equals, let's call it x naught. The procedure is identical, so I can take my x of t, which is a vector of x1 of t, x2 of t, and so on, right? It's a vector. This is, again, b1 plus some b2, no, starting from here, b naught. b naught plus b1t plus b2t2, but remember that these are b naught 1, b naught 2, and so on. All of these are vectors now. Maybe I can write it as capital. Why not? Let's do that to make it look nice. B naught, B1, B2. Okay, that's better. Better notation. So if time is 0, so at x of 0, which is my x naught, will turn out to be the vector b naught. Same thing I had here. At time equals 0. I can again take the derivative, x dot of t. These are all just the vectors of constant numbers, so they can come out of the derivative. So I'll have very similar form as here. I'll have b1 plus b2t, no, b1, 2b2t plus 3b3t2, and so on. Doing the same thing, I can take this one and that one, plug it into my equation. So what do I have? I have, let me write it down, where's b? So b naught, no, starting from here. b1 plus 2b2 t plus 3b3t2 plus dot 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 equals b naught plus b1t plus b2t2 plus dot dot dot, and then making all of these equal exactly the same way. You see where I'm going. So everything looks identical between these two conditions, except my b's are now capital B's, and my A is capital A, representing vectors and matrices. but mathematically they look identical. So from here I can know that my B naught was X naught and my BI for other i's is 1 over I squared matrix A raised to power I times Ti. So this is, for instance, if it's A, it's going to be A times A, that would be A squared, so matrix multiplication. And in the end, my, where was it? Here. My X of T is going to be this X naught. Wait a minute, I'm missing. AI X naught T. No, not T. Well, what did I have? Where am I? BI. Here. X naught. Yeah. That's. Okay. So X naught times the summation of I equals 0 to infinity of 1 over I factorial AI Ti. And that is the solution to this matrix differential equation. If I know the vector of initial conditions with matrix multiplication of A by itself and forming this infinite series, I can find the response. So the analogy here is this one in a scalar form. It was equal to the exponential e to the power at. Here we can do the same thing. We can take this infinite series and call it e kind of to power of matrix A times T. This is very bizarre. What does this really means? Raising a number to the power of a matrix. Who knows what that means? But one thing to remember that this is just an analogy, an analogous way to write the same infinite series. Here we just call this series with this shorthand notation of e to the at. It doesn't really mean raising e to the power of a matrix. It's just an operator that takes matrix A, spits out another matrix. Sorry, this, in order for the dimensions to work, it has to be like this. X naught. So remember, this is E. Also, sometimes it is called or used the notation phi, capital Phi, and it is called state. Does it have a hyphen? I don't know. State transition matrix. So you can calculate your state transition matrix, which is this E to AT, or sometimes use the notation phi, which essentially is an infinite sum. So if you define that, then your x of t, your response is going to be this e to the at x naught. Very similar form as we had here, just in matrix notation. So this is a rather powerful notation, and a lot of intuition and useful results can come out of that. The first intuition that you can kind of make this analogy between the two systems, if you have, in the scalar case, so you have e to the at. Let me draw a thing around it so you know it's important. So e to the at, if a was positive, you had unstable. If a was negative, you had a stable. If they were real, if they were imaginary, again, same situation with the reals, the real part of a. And if you had imaginary parts, a was a complex number, a complex, you would have rotations in your response that your system would oscillate. Similarly, if you have e to the at, if the real part of the eigenvalues of a are positive, or any of them is positive, it's unstable. If the real part of all these eigenvalues of a are negative, you have a stable. And if your eigenvalues are complex, you have oscillation. So this is a very nice way to even remember the relationship between the eigenvalues and the response of the system. Essentially, eigenvalues define how the matrix A behaves, and that is a substitute for the scalar value A. I mean, one last thing to refresh your memories. If A is just a 1 by 1 matrix, eigenvalue is this scalar value A. So, okay. So let me quickly recap what we have done. We have this matrix form of differential equation or system dynamics. We are looking at only the natural response. It's here. You're only looking at the natural response when the input is 0, and as it turns out, we can write the natural response as some kind of matrix exponent e to the at multiplied by the initial condition. That would give us the same response that we would expect in a scalar system. So very similar analogy. Let me check if I'm missing anything. We covered this, we covered that. Okay. So let me clean up the board and I'll come back with a couple of more items and we wrap up this lecture. So I have written the essence of what I just did. I have this differential equation in the matrix form. So I'm going back to use the lowercase notation because I'm going to use the uppercase for something else. But remember that it is now a matrix equation. So I have x dot equals matrix A times x with the initial condition being vector of x naught. And the solution is this e to the at times vector of initial condition x naught. And we saw how we can define this e to the at properly. There is another way we can solve the same problem, and you guessed it, that's where I need my capital letter, the Laplace transform. So I have this equation, x dot equals ax. So x is a vector, x1, x2, and so on. So I'm taking d over dt of this. Let me put it this way, x dot 1 x dot 2, and so on. So taking Laplace of this is going to be, let me do this, Laplace. I can take Laplace of individual elements. So it's going to be s x1 of s minus x x1 of 0 s x2 of s minus x2 of 0, and so on. And this one becomes s. I'm factoring out all the s's and keeping the initial condition as another vector. So I'll have s x of s, a vector of all these x1, x2, and x until xn of s, minus x naught, which is the vector of all these state variables at time 0. So that is the Laplace transform of that side. The right hand side is just a constant matrix times times vector x. So after I do all the Laplace transforms, the a, because it's constant, can come out again. So in the end, the Laplace transform of this equation is going to be s x of s minus x naught equals a x of s. Or I take this to the other side, that one to this side, so I have s x of s minus a x of s equals x naught. S is just a scalar value, it's the Laplace variable. So I can write it as si minus a times x of s equals x naught. And I'm going to multiply by the inverse of si minus a, hoping that it is invertible. And remember, it is only not invertible in the eigen when s equals one of the eigenvalues of a. So other than that, for all other s values, this matrix is invertible. So x of s equals si minus a inverse times x naught. And again, to emphasize, all of these are matrix manipulations. And finally, I now have x of s in Laplace domain. Now take the inverse Laplace. I take the inverse Laplace of this equation. On the left hand side I have x of t equals inverse Laplace of this. Let me write it. Inverse Laplace of how do I do that? Bigger one. Si minus a inverse. So Laplace inverse of that inverse times, and x naught is just a vector of constant value. So these are all the x1 and x2s, x naught. So where are we at? I use Laplace transform to solve this differential equation. And I arrived at this solution, and comparing it with that, now I can, let me write this one here. So from before we had x of t equals e to the at. Oh, okay. Let me see. Notation wise, sorry to confuse you. Let me make this little x because it's not in Laplace domain. So let's call it little x naught. That's the ugliest x. Little x naught, little x naught, little x naught. Am I missing anything? No. little x naught. This one also little x naught to have good notation. Good notation matters. So from one solution I arrived at this, from the other solution I arrived at that, which means my state transition matrix e to the at equals Laplace inverse of Si minus A inverse. So this is another way we can calculate the state transition matrix. Good. All right. So that's that. I leave it at it. To be honest, I don't know exactly how you can make use of that, other than there are two ways you can define the state transition matrix, one from the infinite series and one from the Laplace inverse. But let's keep it as is. What else? We did this, we did that, the state transition matrix. Good, okay. So now we know how we can find the natural response of a matrix equation. We can use the state transition matrix e to the at multiplied by the vector of initial conditions to get the response for all time t. Now this begs the question, what if there is input? So if we have input, we are looking at the forced response and how we can extend kind of these ideas to the forced response. So it is going to be a little, not too involved, but it involves convolution. Let me maybe write it down and then we can make sense of it, try to make sense of it. So if I have input, I have then my equation is like that. X dot equals ax plus bu. I might still have some initial condition, x of 0 equals some x naught, but here u is not 0. In this case, the solution x of t is going to be a combination of the natural response and forced response. The natural response is the same thing we had here, e to the at times x naught, plus the forced response is going to be a little funny looking, but hopefully you have seen it before and it makes a bit sense to you. B times u of tau. Probably this has to be on the other side. So e to the t minus tau, b u of tau d tau. So I'm sure you have kind of seen this before, at least I had a mini lecture on it. This is the convolution of, oh wait, I'm missing an A. This is the convolution of the function e to the at and bu and let's see why we have that. Before getting into long story short, this is how you can find a solution to any arbitrary input u, and from any initial condition x you can find the full response x of t. And that's the end of the story. The rest of it is intuition why this works. So before I can, let me start with this. So imagine I have kind of arbitrary input u. This is in a multi-dimensional, so u could be a vector, but let's, for the intuition, look at just a scalar u. This u, I can write it as a series of impulses that are stacked next to the other to create this waveform or pattern of u. So I have, let me write it a bit smaller. So this u is equal to this plus that plus this and so on. So I'm stacking a bunch of impulses, one after another, happening at time tau. So because of each of these impulses, I may have, so starting from tau, I may have a kind of response. So I don't know how they will look like, but so this one goes here, something like that. So if I apply my impulse to the system, I get some kind of response. And the same way, because the system is linear, by summing all these inputs, I get the original input. The same way, by summing all these individual responses, I get, if I sum all of these together, I get my full response x of t, right? So that's the intuition we are going to use. And another thing to remember, I left it here to write it down. If I take Laplace of this equation, so I have s x of s here equals a, well, let me give it the initial condition, minus x naught equals a x of s plus b u of s. And I can bring this to the other side, so s x of s equals a x of s plus b u of s plus x naught. So if I have x naught and no input, I get the response that looks like this, the natural response. But if I have u, and u is an impulsive function, and no x naught, so I'm looking at just an impulse response, it is possible to find an equivalent x naught. So if, let me write it down, if x naught is 0, but u equals some u of tau delta of t minus tau. So I'm taking the value of u at that point and making it an impulse. So in this case, my equation s x of s equals ax of s plus b, what do I have? B u of tau, and the Laplace of impulse is 1, but I have this time shift t minus tau, and that gives me u of tau. This is just a number. Laplace of that is 1 times e to the minus s tau. And so this is the equation that I should really be solving to get any one of these responses. But compare this equation with that equation. So s x of s, sx of s, ax. So this means that this one acts similar to some kind of initial condition. Let's call it x prime, x naught prime. So if you give your system an impulse, it is very equivalent to releasing the system from some initial condition that, let me write it down, I'm not sure if you see it. X naught prime. Giving it an impulse is equivalent to starting from an initial condition. This should be up to here. But note that I have this term that came because of the delay. So it was t minus tau. That's why this showed up. So this equivalent system, so for any of these, I'll have some e to the a t minus tau multiplied by this x naught prime. So depending on how much time has passed since the time of the impulse, multiplying that by the equivalent initial condition, or maybe even I don't know if you see it. Let me write it a bit better. So e to the a t minus tau x naught prime, and this x naught prime is b u of tau, the strength of the impulse at that time. So it is going to be b u of tau. Again, I don't think if you see it, so times b u of tau. So similarly for all these other responses due to impulses, I get a similar equation. Now what I need to do is sum all of these together to get my full response. So if I sum them, and sum becomes in the form of an integral, I have e to the a t minus tau b u of tau d tau, and this is the force response. Oh, come on. Force response, which is exactly the same thing as I had here. So force response plus the natural response gives me the full response. So this breaking down input into a series of impulses is a good way to try to intuit why this convoluted form, because it's a convolution, this convoluted form comes into play. Okay, so that's all I have for now. These are analytical methods, and depending on what field you are in, you can take this e to the at and do something with it for the analysis or control design and things like that. But for now, we'll leave it as is. So I just wanted you to know what the state transition matrix is and how you can find it to find the natural and forced response of the system. But in practice, at least my own practice, I always work with numerical solutions of the system. I don't do as much analytical work with the state transition matrix. But that doesn't mean not everybody does that. Many people use it and it's powerful. Especially if you want to kind of prove a stability or do some kind of analytical results. You need analytical results about the system. Okay, so that's all for now. And I think the only last thing for this state space analysis is frequency response, which comes next. And until then, enjoy